We are now going to look at LL parsing for context-free grammars. In contrast to the CYK parsing algorithm for context-free grammars, LL parsing is more efficient. However, LL parsing has one big drawback, namely it does not work for every context-free grammar. We are now looking at top-down parsing algorithms. That means we are starting from the starting variable and we try to derive the input word. The simplest possible strategy would be the following. We look at our derivation and we almost expand the leftmost variable. So if our leftmost variable is a and we have a production rule a rewrites to u, then we replace our leftmost variable by u. What do we do if we encounter that we have derived a mismatch, so we have derived a letter that does not match with the input? Then we are going to backtrack, so we are undoing the replacement, and we try another production rule. So this is very simple, but it has one disadvantage, namely that the backtracking is difficult and it's very expensive. So actually with backtracking you can get exponential time complexity with respect to the length of the input word. LL parsing is a top-down parsing technique with a leftmost strategy, so just like on the last slide, but now backtracking is strictly forbidden. So LL parsing does not apply backtracking. That means that whenever we unfold a variable, there has to be a unique choice for which rule to apply. And how does this work? LL parsing just looks a few letters ahead in the input, and these few letters ahead need to uniquely determine what rule to apply. And as a consequence, LL parsing is very efficient, but it does not work for every context-free grammar. If it works, then it's a very nice and efficient parsing algorithm. What's the starting point for LL parsing? The starting point is a context-free grammar from which we have removed all the useless variables, but lambda and unit productions do not need to be removed. Actually, it's not good to remove them because they could increase the size of the grammar. And for LL parsing, this could make things more inefficient. So we leave the lambda and unit productions in the grammar, but we remove the useless variables. And we will see on the next slide how this is done. LL parsing consists of the following three main steps. We compute first sets and follow sets for every variable. We construct a parsing table, and then we parse the input using the parsing table. So the first step of LL parsing is the removal of useless variables. A variable a is said to be useless if there exists no derivation from the starting variable to a terminal word that uses the variable a. So if a is never appearing on a derivation from the starting variable to a terminal word. So clearly, if you have a variable that never appears in such a derivation, then this variable is useless. You can drop it and you can drop all the rules that contain a without changing the language generated by this context-free grammar. So let's have a look at an example. What are the useless variables in this example? For one, the variable a is useless because we can never reach the variable a from the starting variable. We cannot produce a from the starting variable. There's no right-hand side that contains the variable a. So a is useless. We can drop a and we can drop this rule. Also, the variable c is useless. C can be produced. There is a rule from S we can get to C, but once we have produced C, we can never reach a terminal word. C just rewrites to itself. So if we have derived a word with the variable C, we cannot get rid of C. We can never get to a terminal word. So it can never appear on a derivation from the starting variable to a terminal word. So C is useless as well. Now, because C is useless, also the variable B is useless, because the variable B can only be reached together with C. So whenever we have derived a word with the variable B, then there's also a C, and from C we cannot get the terminal word, so B is useless as well. So actually A, B and C are useless, so we can drop all rules that contain A, B or C. What remains is just two rules, namely S rewrites to terminal A as terminal B or to the empty word lambda. So how to determine the useless variables of a context-free grammar? We will do this in two steps. First, we are going to determine the productive variables of a context-free grammar. We say that the variable A is productive if there is a derivation to a terminal word. So clearly, if you have a variable that does not admit the derivation to a terminal word, then this variable is useless. So the non-productive variables are clearly all useless. How do we determine the productive variables? We look at all the production rules of our grammar, and if we have a production rule in which all variables in the right-hand side are known to be productive, then also the left-hand side is productive. So in particular, if the right-hand side contains no variables, so if the right-hand side is a terminal word, then the variable in the left is productive. But also then, if we know already that a certain set of variables is productive, and we have a rule where there's only terminal letters and productive variables in the right-hand side, then also the left-hand side is productive. So once we have determined all the productive variables of our grammar, we can throw away all the rules that contain a non-productive variable. Because if we have a rule that produces a non-productive variable, then from this non-productive variable we will never be able to get to a terminal word, so this rule cannot contribute to the language of the grammar, and we can drop it from the grammar. So we drop all the rules that contain non-productive variables. Next, we are looking for the reachable variables of the remaining grammar. So what are the reachable variables? We look at the reachable variables from the starting variable s. So the starting variable s itself is always reachable. And if we have a reachable variable a, then all the variables in the right-hand side of a production rule with left-hand side a are also reachable. If a is reachable, then anything in the right-hand side is reachable as well. Now we use this to determine all the reachable variables of our grammar, and then we drop all those rules that contain a non-reachable variable. So if you have a variable that is not reachable from the starting variable, then this is useless and you can drop the rule from the grammar. Now, after having dropped all the non-productive variables and all the non-reachable variables, what remains are the useful variables. So a variable is useless if it's not in one of the remaining rules. So all variables of the original grammar that are not in one of the remaining rules are useless. For this algorithm to work, it's important that we first drop the non-productive variables and then the non-reachable ones, because dropping the rules containing non-productive variables may influence the reachable variables. Because we drop certain rules, more variables may become unreachable. So it's important to keep this order: first drop the non-productive variables and then the non-reachable variables. Let's have a look at our grammar again. We start by determining the productive variables. So B is clearly productive, it rewrites to a terminal word. S is productive, it rewrites to a terminal word, and because S is productive, also A is productive. So A, B, and S are productive. So the non-productive variables is just C. C does not rewrite to a terminal word. So C is not productive, so we remove all rules from our grammar that contain C. We remove this rule, and we remove this rule with right hand side BC, because also this contains a non-productive variable C. So this is our remaining grammar, and now we determine all the variables that are reachable from the starting variable S. So clearly S is reachable, and from S we can reach just S, nothing else. So neither A nor B are reachable from S. So we drop all the non-reachable variables. What remains is just the two rules for S. So if we look back at our original grammar, then we can conclude that the variable A, B, and C are all useless. And in this example, you also see that it's important to first remove the non-productive variables, followed by the non-reachable ones, because originally the variable B was reachable from S. Only after having removed the non-productive variable C, B becomes unreachable. After having removed all the useless variables, we are ready to compute the first sets. So the idea of the first sets is as follows. First of a word W is the set of all terminal letters that can appear as first letter of a word derived from W. So we start by W, we take all the words that can be derived from W, and we pick all the first terminal letters of these words. Additionally, we say that lambda is in the first set of W if lambda can be derived from W. Now, how do we compute this first set? This does not help much, it gives us an idea of what we want, but in principle this could be an infinite set of words that is derivable here. So we are going to compute this in two steps. First we are going to compute a set pre-first of W, and that's computed using these clauses. W is always in the set pre-first of W, and if we have a word AV in pre-first of W, and A is a terminal letter, then also A is in pre-first of W. If we have a word BV in pre-first of W, B here is a variable, then also B is in pre-first of W. So the first letter of any word in pre-first of W is also in pre-first of W. If we have a word BV in pre-first of W, and the variable B is erasable, so if it rewrites to lambda, then we also put V in pre-first of W. If we have that a variable A is in pre-first of W, and there is a rule A rewrites to V, then we also put V in pre-first of W. So we will see on an example on the next slide that these clauses are actually quite intuitive. Now, once we have computed pre-first of W, we derive first of W from it as follows. We take all those terminal letters that appear in pre-first of W. So all terminal letters that are in pre-first of W are also in first of W. Moreover, we put lambda in first of W, if the word W consists only of variables and all of the variables are erasable. So, and this is actually an important point, namely, it could be that lambda appears in pre-first of W, but lambda is not necessarily in first of W. Lambda is added to first of W only if the word W itself consists only of erasable variables. So only if W itself rewrites to lambda. In pre-first of W, we may have lambda for a different reason, because here we are also taking, for instance, variables that are the first letter of a word in pre-first. So it could be that this variable rewrites to lambda, but not the entire word W rewrites to lambda. Let's have a look at an example. We determine the first sets for this grammar. We begin with determining the erasable variables. Clearly A is erasable, S is not erasable, and B is not erasable. So only A is erasable in this case. Next, we determine the pre-first sets. We begin with pre-first of A. Clearly A is in pre-first of A. From A, we get BA and we get lambda, because we have a rule, A rewrites to BA and A rewrites to lambda. From BA, B is not erasable, so we don't get terminal A, but we get the first letter of this word, so we get B. From lambda, we don't get anything else. From B, we get AB, because we have a rule, B rewrites to AB, and we have a rule, B rewrites to D, so we get AB and we get D. Now from AB, we get A already in our set, and because A is erasable, we also get B. From D, we only get D, it's already there, and from B, we only get B, which is already there. So let's continue with first B. First B contains B. From B, we get AB and D. From AB, we get, because A is erasable, we get B. And we get A itself, the first letter of this word. So since A is in the set, we know that all of pre-first A must be in the set. So we can take just the union with pre-first A, which we have already computed. And this gives us this set. So pre-first B contains pre-first A because we have an A in here. Likewise, pre-first A contains pre-first B because we have a B in here. So it's not surprising that these two sets are the same. Now let's continue with pre-first of S, contains S. From S we get AAC. From AAC we get AC because A is erasable. From AC we get C because this A is erasable again. And we of course get A because it's the first letter of AAC and it's also the first letter of AC. And because we have A here, we also get the entire pre-first A. So again, we can just take everything together, which gives us this set. Now, from these pre-first sets, we can derive the first sets for A, B, and S. The first set of A contains all the terminal letters in pre-first A, so that's D and B. D and B must be in. What about lambda? Lambda should be in first of A only if A is erasable. And indeed, A is erasable, so also lambda should be in there. So we get BD lambda. First of B contains all the terminal letters in pre-first of B, which is the same as pre-first of A. So again, we get B and D. What about lambda? This time lambda is not in the set because b is not erasable. So we only get b and d. So observe, although pre-first of A and pre-first of B are the same, first of A and first of B are different. They differ in lambda. Lambda is only in first of A because A is erasable but B is not. For first of S, we get the terminal letters B, D, and we get C. So we get B, C, D, and S is not erasable, so we do not get lambda. So we have computed the first sets. Next, we are going to compute the follow sets. If our grammar contains lambda productions, then the first sets are not yet sufficient for predictive parsing. Then we also need to compute the so-called follow sets for every variable A. Follow of A consists of all terminal letters that appear directly after the variable A in a word derivable from the starting variable S. So we look at all words derivable from the starting variable and we take all terminal letters that follow directly the variable A. So again, this is not good enough for computing these sets because we possibly have to consider infinitely many words. So how can we compute this? We can compute this using the following algorithm. In this algorithm, we use the dollar symbol as a special end of word symbol. So for the variable S, there's always the dollar symbol in the follow set. So follow of S always contains the dollar symbol. I'm writing here the superset, indicating that it could be a bigger set derived from the other rules, namely follow of a variable A always contains the following, namely if we have a rule B can rewrite to VAW, so the word W follows the variable A, then any terminal letter that is in the first set of W, that can be the first letter of a word derived from W, can follow the variable A, except for lambda. So if we have such a rule, then everything in first of W except for lambda must be in follow of A. And the third clause that we will use is this one. If we have a rule B can rewrite to VAW and the word W is erasable, that means that lambda is in first of W, then if this W can be erased, also anything that can follow the variable B can follow the variable A. So follow B must be a subset of follow A. Or put differently, anything that can follow B can also follow A. Let's have a look at some examples to understand the use of the second and the third clause. In these examples, we assume that we have the rule C rewrites to AB. The first example illustrates the second clause. It says that anything in the first of B must be in follow of A. Anything except for lambda. So anything that B can rewrite to, any terminal letter that a word derived from B can start with, must be in follow of A. So for instance, if we have a rule B rewrites to AW, then the terminal letter A is in first of B, and this terminal letter A must be in follow of A. Why is that? Because we can replace C by AB, and we can replace B by AW, and then we see that the terminal letter A follows the variable A. And in general, any terminal letter in first of B can follow A. This example illustrates a use of the third clause. It says that anything that can follow C can also follow B. So anything that can be behind C can also be behind B. Namely, if we replace C by AB, then anything that was behind C is now behind B. You see this if you assume that you have also a rule S rewrites to CA, then the A is in follow of C, because the terminal letter A can follow C. And it must also be in follow of B, because we have the following derivation, S rewrites to CA, and then we can replace the C by AB, and now the terminal letter A is following the B. The third example illustrates also the third clause, but now slightly more involved, namely that everything in follow of C must also be in follow of A if the variable B is erasable. For example, assume that we have a rule S rewrites to CA and B rewrites to lambda. Then we have the following derivation. S rewrites to CA, so the A follows C. Then we'll replace the C by AB, so now the A follows the B, but B is erasable, and if we erase B using B rewrites to lambda, then the terminal letter A suddenly follows the variable A. So if B can be erased, then anything that's behind C can be also behind A, so follow of C must be a subset of follow of A. Let's have a look at an example grammar. So here we have already computed the first set, and now we are going to compute the follow sets. For follow of S, we definitely get the $, the end of the word symbol. Now we have to check whether S appears in the right hand side of a rule. This is not the case here, so we only get the $, for S. For D, we have one occurrence in the right hand side, and this occurrence of D is followed by the word C, so we have to take first of C into follow of D. First of C is just C. Now, if this C would be an erasable variable, then we would also have to take up follow of S into follow of D. In this case, C is not an erasable variable, so we have nothing more to add to follow of D. For follow of A, we now have multiple occurrences of A in the right hand side of a rule. Let's start with this one. This occurrence of A is followed by a word A, so we have to take first of A without lambda into follow of A. So we get first of A without lambda must be part of follow of A. Now, because of this occurrence of A, which is followed by a word B, we must take up first of B. This is also this second clause. We must take first of B without lambda into follow of A. First of B is just B. For this occurrence of lambda, this is followed by an empty word. So first of the empty word is just the empty word, but we exclude from the second clause the empty word, so this gives us nothing new with respect to the second clause. However, we still have to consider the third clause, and we have two applications of the third clause here. In this case, the third clause is not applicable because the B is not erasable. But we can apply the third clause for this occurrence as well as for this occurrence. So let's start with this occurrence. This occurrence is at the end of the right hand side, so it's followed by the empty word lambda. So clearly lambda is in first of W, lambda is in first of lambda. So whatever follows D can also follow this occurrence of A. So we have to take follow of D up into follow of A. The third clause is also applicable for this occurrence of A. Because this A is erasable, so it rewrites to lambda, anything that can follow D after erasing this variable can also follow this variable. So this is another reason that follow of D needs to be taken up into follow of A. Okay, so follow of A is composed of first of A without lambda, B, and follow of D. We know what all of these are, so we get B, C, and D. Now we have to compute follow of B. We have one occurrence of B in the right hand side of a rule. This occurrence of B is followed by the word A. This gives us the second clause. In the second clause, the A is now the W. So first of A just consists of A. So follow of B just consists of the single letter A. Now we have computed the first set and the follow set, and we are going to use this information in order to create a parser table. A parser table for a context-free grammar is a table that has columns indexed by terminal letters and dollar, and rows indexed by all the variables of the grammar. And we now fill each cell in this table by a set of rules of the grammar. And what rule do we put in what cell? This is defined here. We look at the cell in column A, so A is a terminal letter or dollar, and in row B, so B is a variable, so we look now at the cell indexed in column A, row B, and we put in this cell all the rules B rewrites to U, where the following holds, so one of these conditions. Either the column index A is in the first of the right hand side of the rule U, so A is in first of U, U is the right hand side of the rule that we look at, or the right hand side of the rule is erasable, so lambda is in the first of U, and the column index A is in follow of the variable B that we look at. So now let's apply this to this grammar here. We are looking at this cell first. It's indexed by the terminal letter A and the variable S. We have two rules that we have to consider. First, we have the rule S rewrites to ASB. So should the rule S rewrites to ASB be put in this cell? Yes, because we are in the first clause. The terminal letter A is in first of the right hand side, so A is in first of ASB. So since A is in first of ASB, this rule needs to be in this cell. Now let's have a look at the second rule, S rewrites to lambda. Should this also be in this cell? Should there be two rules in this cell? We don't have the first case, so A is not in first of lambda. Let's have a look at the second clause. Now lambda is in first of the right hand side. Lambda is in first of lambda. Is A in follow of S? A is not in follow of S. So S rewrites to lambda is not part of this cell. Okay, let's look at the next cell. So here we have a cell indexed by B and variable S. We look at the first rule, S rewrites to ASB. Is B in first of ASB? No, first of ASB only contains A. B is not part of first ASB. So the rule S rewrites to ASB should not go into this cell. The second clause is also not applicable to the first rule because lambda is not part of first ASB. ASB is not erasable. Okay, so let's look at the second rule, S rewrites to lambda. B is not in first of lambda, so we are not in the first clause. Let's look at the second clause. Lambda is in first of lambda, so this is true. And we have to check whether B is in follow of S. B indeed is in follow of S, So S rewrites to lambda should be part of this cell. And finally for the dollar is never in first of the right hand side. So the first clause can never apply to dollar, but we can be in the second clause. So we look at rules where the right hand side is erasable. There's only one such rule, namely S rewrites to lambda. So we have to check whether dollar is in follow of S. Indeed, dollar is in follow of S, so S rewrites to lambda should go into this cell. So this is the completed parser table for this grammar. A context-free grammar is said to be LL1 if the parser table that we've computed contains at most one rule in each cell. The name LL1 hints at the fact that we are reading the input from left to right and that we are performing a leftmost derivation strategy. So we always unfold the leftmost variable. The 1 hints at the fact that we are using a 1 symbol look ahead. So we never look more than a single symbol ahead in order to determine what rule we apply. Let's see how this works. So we have given an LL1 grammar, we've constructed our parser table, and now we want to parse an input word A1 up to AN. So we start with the pair consisting of S dollar and our input word followed by dollar. So you can understand this as follows. We want to derive from S the input word A1 up to AN. Now, how do we proceed in each step? If we are in a state some pair VW, then we proceed as follows. If both entries of our pair start with the same terminal letter A, then this matches nicely. We can drop the A and continue with the remainder. If the first entry of our pair starts with a variable B and our input starts with a terminal letter A, then we look in our parser table at the position AB. So we look in the parser table at position AB. We look what rule to apply to variable B in order to derive an A. If there is a rule in the parser table at this position, let's say the rule B rewrites to U, then we apply this rule to B. So we replace B by U. If there is no rule in the parser table, then we are stuck and we reject. If we have a variable B in the first entry of the pair and a dollar in the second entry of the pair, then we look at the position $B in our parser table. And if there is a rule B rewrites to U, then in principle you can do the same as in the second case. You could replace the B by U. However, if the input is $, then we anyway know that we want to derive the empty word. And the only rules that can be in the column $, are those rules where the right hand side of the rule is erasable, so rewrites to the empty word. And this is anyway what we want to do here. We want to rewrite this left side of the pair to the empty word. And if there is a rule at this position in our parser table, then this means B can be rewritten to the empty word, so we can immediately drop B. If we reach a state where we have a pair $, then we accept the parsing has been successful. We have successfully derived from the starting variable our input word. We have matched all the input letters and dropped all of them, and we accept. In any other case, we reject. So now let's look at an example. We've seen this grammar before and we've already computed our parser table. Now we want to parse an input word. Let's start with the input word AB. So from the variable S, we want to derive the input word AB. and we do so by using the parser table. So the left entry of our pair starts with a variable s. The first letter of the input is an a. So we look in our parser table, how do we get from the variable s an a? The parser table tells us we have to apply this rule. So we use this rule and we apply it to s. This gives us ASB $, AB $. Now the first letter of the left and the right entry of the pair matches, so we can drop this terminal letter A. Now we have SB $, B $, so we have a variable s and input letter b. So from s we want to derive b, we look in our parser table at position SB, and the parser table tells us we have to apply the rule s rewrites to lambda. So we apply this rule and we rewrite s to lambda. Now the b matches, we drop the b, we get $, and we accept. We've successfully passed the input AB. Let's try to pass the input word ABB. Again, we have variable s and we want to derive input letter A. So we look at position SA in our parser table, and the parser table tells us we have to apply this rule. We apply this rule to s, gives us this. The letter A matches again, we drop the A. Now from s we want to derive a B. We look in our parser table at position SB. We have to apply this rule, so we replace s by lambda. This gives us this. Now the B matches, we drop the B, and we get $B $. At this point there's nothing we can do, so we have to reject. Let's try one more input, namely let's try to pass AAB. So from s again we want to derive the input letter A. We look at position SA in our table. We apply this rule to s. The A matches again. We drop the A. From s we want to derive again an A. So we again look at position SA. We apply this rule to s. So we get ASBB $, AB $. The A matches again. We drop the A. From s we want to derive a B. The parser table tells us the only way to do this is by rewriting s to lambda. So we rewrite s to lambda. We get BB $, B $. The B matches can be dropped. So we get B $, And again, at this point, there's nothing we can do. So we have to reject. And indeed, only AB was successfully passed. And indeed, only AB is in the language generated by this grammar. ABB or AAB are not in the language. So it is correct that we have rejected them. So for instance, these LL1 grammars are used in Java CC for automatically generating a parser. LL1 grammars only use a single symbol look ahead in order to decide what rule to apply. This can be quite limiting in practice, and there's a generalization of LL1 which is called LLK. LLK parsers look K symbols ahead in order to decide what rule to apply. So the parser table for LLK is constructed with a K symbol look ahead, and we say that the grammar is LLK if this parser table contains at most one rule in each cell. Increasing the K gives strictly more power. However, it has a severe disadvantage, namely that increasing the K yields an exponential growth of the parser table. In practice, what really helps is also that we are operating on tokens. So we have discussed lexical analysis, which transforms sequences of characters into sequences of tokens, and then defining an LL1 grammar on tokens is much more powerful than defining an LL1 grammar on just single characters, because a single token look ahead is more than a single symbol look ahead. Let's do two simple exercises. The first exercise asks, can ambiguous grammars be LLK for some k? And the obvious answer is no. If you have an ambiguous grammar, that means that you have some input word that has two derivation trees. And then for this particular input word, no matter what look ahead you have, there's always a choice in what rule to apply, because you have two different derivation trees that give the same word. So no matter how high k we use, the look ahead will not be sufficient to uniquely determine the rule. That means ambiguous grammars can never be LLK for any k. What about this grammar? This grammar is not ambiguous, so we have S rewrites to A as A or S rewrites to lambda. So this grammar generates words over A that contain an even number of A's. Is this grammar LLK for some k? And also here the answer is obvious. It cannot be LLK for any k. So if you pick any k, then if we generate a word that is longer than, let's say, 2k, then with the look ahead of k, we can never be sure whether we are before the middle of the word or after the middle of the word. So with this look ahead, we cannot know whether if we are before the middle of the word, we should apply the first rule. If we are behind the middle of the word, we should apply the lambda rule. We should remove the s. But with the look ahead of k, we cannot decide whether we are before or after the middle. So also this grammar cannot be LLK. No fixed look ahead is enough to decide what rule to apply. This grammar that we've seen here is not LLK for any k. However, we can transform the grammar. We can change the first rule instead of A as A. If we change this to AAS, then the resulting grammar generates the same language, namely words only consisting of an even number of A's. But the changed grammar is LL1. If we have the rule S rewrites to AAS, then we can keep applying this rule until we reach the end of the word. So with a one symbol look ahead, we can decide whether to apply the first or the second rule. Similarly, sometimes grammars can be transformed into LL1 by what is called left factorization. Left factorization is a transformation of context-free grammars that can help to make a grammar LL1 or in general LLK. So let's assume that we have two rewrite rules that have the same left-hand side A, and they both, the right-hand side starts with some non-empty word u. So u is a shared prefix of the right-hand side. Now this grammar is not LL1, because if the input starts with a letter, the first letter from u, then we cannot decide whether to apply the first or the second rule. However, we can transform this grammar in such a way that it may become LL1. The idea is that we introduce a fresh variable b, and we say that a rewrites to ub, so u is this common prefix. And after having produced u, then b takes care of producing either v or w. So let's have a look at an example. Here we have such a grammar. So we have S rewrites to AB or to AC. This grammar is not LL1 because we have two rules in one cell of the parser table. However, if we apply left factorization here, then we can split these rules. We introduce a fresh variable, so we say that S rewrites to A, so terminal A, variable A, and the variable A then rewrites to B or C. The language generated by the grammar is the same as of our original grammar, but now the grammar is LL1. Now with a single symbol look ahead, we can always decide what rule to apply. If we have a variable s and we see an input letter A, it's clear that we have to apply this rule. There's only one rule for s. And then if we see a B or a C, we know whether to apply the first or the second rule for A. So left factorization is a transformation that can sometimes help to transform a grammar into an LLK grammar, and in particular in this case an LL1 grammar.